Mm, Hello, Mary. Can you hear me?
Yes. Hello.
Yeah. Hello. So we are going to wait for like 3 more minutes for other people to arrive, and then I'll start the session. Is that fine?
Okay. Okay.
Okay. So I think I'll start now. So this week's lectures were in continuation with previous week. So previous week you studied about DC motors, permanent magnet DC motors, and brushed permanent magnet DC motors. So this year's lectures were mostly towards brushless DC motors. So we'll be just doing some basic problems related to brushless DC motors. So I'll need some of your inputs, okay, for this to work.
Okay.
Yeah. So here's the first problem that we'll be doing. Like you studied about the back EMF, right? Back EMF curve for a VLDC motor and a PMSM motor,
Yes.
right?
Um.
So like, can you answer this question? Like, what is the angular interval over which the waveform is induced? The induced waveform basically remains flat over one cycle.
Uh. No, I didn't. No, I don't know about it.
Okay, didn't okay. So these are the back EMF curves for a VLDC motor. Can you see them?
O- Okay.
Yeah. So basically, the question is asking, so from 0 to 360 degrees, for how many degrees is the curve flat?
Okay.
Yes. So in one full rotation, basically, how
Okay.
much portion of the back EMF profile is flat?
Okay. That is from 0 to
Yeah. So from
120.
yeah. So from
Wait,
yes.
and again from 300 to 360.
So you see, so yeah, how much is it?
S- I know, I don't know.
So it turns out to be 300 degrees, right?
Okay, okay, yeah.
Okay,
300 to 360.
yeah, but that is wrong. Okay, because for the correct estimate, you should look at the third one, phase C of winding A. Okay,
Okay,
between phase C and A. Okay, because in the first one also there is a curve that is, you know, going below. That is basically increasing towards the 0 degree mark. Okay, so that is where the curve has to start. Okay, so when you see from the third curve, you can see that it is flat for 240 degrees out of 360 degrees,
okay,
right? So basically, in one go, it is flat for 120 degrees, and total in 360 degrees, it is flat for 120 plus 120, that is 240 degrees.
okay.
Okay, you can see my mouse, right? My mouse pointer.
Yeah, yeah.
Yeah. Now the question comes: why is the flat part important? Yes.
I didn't gone through like the subjects related to the electrical part.
Oh, okay. Did you go through the lectures that were there?
Uh, Not this week. Only not this week. Not this week lectures.
Oh, okay, okay. Not this week lectures. Okay.
Okay. Uh,
Okay, so but you do know about back EMF and all, right?
yeah, I just know the basic concepts of that.
Okay, then then I'll just tell you this, like, so we are interested in the flat part because this flat part gives us the amplitude of the back EMF, and the
Okay,
amplitude of back EMF is directly related to the angular velocity of the rotor. Okay, basically the speed of the rotor.
okay.
Okay, so like say let's say you know what an oscilloscope is, right?
Okay, yeah.
Right? That instrument in which we have two probes and then we connect it to any voltage source and then we can see the voltage profile on that,
Yeah, I know. Yeah.
right? So
Yeah.
basically, if you see, let's say you're running a BLDC motor and then you connect that oscilloscope to any, let's say phase AC of the motor, and then you see this back EMF profile. So then from this profile, you can calculate that what is the speed at which it is running.
Okay, okay. I got it. Yes.
Okay. Yeah. So yeah, but see, most of the problems that we we do in the start are actually forward problems. Okay, that
Okay,
given the angular velocity, what is the back EMF, right? But
okay,
like practically, the more important problem is the inverse problem. That given the back EMF, what is the angular velocity?
okay,
Okay, so that is why the flat part is important.
okay. So we have some sort of equation for that.
Some sort of equation for what?
Uh, so I know till regarding the like off bridge.
You know about H bridge, right?
Yes, yes, off bridge, and
Okay.
I know until that, but after that, I didn't gone through all the concepts.
Okay, okay. Actually, see, if so, basically, for each motor, the relation between this amplitude of back EMF and
Okay,
the angular velocity is different. Okay, so there is a constant that is specific to each motor.
okay,
Okay, so but basically, if you want an equation, then you can write something like this: that let's say the amplitude of back EMF, that is EF. Okay, that is equal to uh, Yeah, that is equal to some constant times the speed,
Okay.
right? So um, basically these are the this is the only equation that I can give you, because also the frequency of this back EMF plot, okay, the frequency of this plot, okay, that is also proportional to omega, and in fact it is equal to omega. Makes
Okay.
sense, right? Because
Okay. Yeah.
the faster the motor rotates, the faster the back EMF will change its directions, right?
Yeah.
So that is that. So now, like this thing will come in the next problem also actually. Okay, this how would the magnitude of the flat portion, okay, and the frequency of induced EMF in a BLDC motor change if the speed of rotor is increased to 3 times? Okay, so can you answer this?
Magnitude of.
Okay, so basically, if I will draw for one phase, okay, the back EMF profile. Okay, so this like this, right? And we said that this was 360 degrees. Okay, so this amplitude, let us call it EF. Okay, how would this amplitude and the frequency? Frequency is 1 over time period, so time period is 1 over frequency. Any doubt in that?
No. No.
Right? So how would the amplitude and the frequency change? Okay, if I, let's say, change omega, let's say new speed is 3 times the previous speed.
Okay.
Okay, so I had written some equations here.
Yes.
So can you guess, if I make my omega 3 times, how would the amplitude and the frequency change? Yes,
Uh.
see, your EF is, let us say, some constant times omega.
Omega. Okay.
Okay, let us say the initial velocity was omega 1 and the final is omega 2. Let us not do pranks for now. Okay, so EF1 is the same k times omega 1.
Okay.
Okay, and then I'm asking you what will be EF2, okay, for the same motor. If the motor is same, then k will not change.
No. That's just 3 times.
Okay, yeah, basically EF2. Now, since you have said, I will just write. Okay, it will come out to be just 3 times EF1.
Yes.
Okay, and same with the frequency. Okay, because frequency is directly equal. Okay, you can also say it is proportional, but also it is equal to the angular frequency. Okay,
Okay.
so
Okay.
yeah, basically this is something that we always remember intuitively. Okay, that if the back EMF increased by, let's say, 1.5 times, then our speed has increased by 1.5 times. Or you can see anything. Either you can see the back EMF, okay, or you can see the frequency.
Okay.
Okay, now do you have any idea, like how does how can frequency give you like how would you measure the frequency of this plot? Okay, what would be an easier way?
Fre-
Okay, like before that, since we have two ways to calculate the angular velocity, one is either I can measure the amplitude or I can measure the frequency. Okay, so which one of the two would be more reliable? Hmm.
Maybe the amplitude.
Why? Okay, so I'll tell you. See, this frequency, basically the timing of this entire circuit is being controlled by a very high frequency oscillator. Okay, and that is very accurate. Okay, but the voltage sensing, okay, the value of this voltage we are getting through some different electrical components that are not that accurate. Okay, because there, all, if you might have used oscilloscope sometime, there is a lot of noise in the signals, right?
Okay. Oh yeah.
Okay, so basically frequency is actually a good measure if you want to calculate the angular velocity. Okay, now how do you measure frequency? Okay, so basically this graph will keep going like this. Okay, it will just continue forever. Okay, so one thing I can do is I can accurately determine where is the midpoint of this slant line here, and then midpoint of this one more slant line here. Okay, and then I measure the time difference between them, right?
Okay.
If I know this delta t, then I can do 1 over delta t. That will give me f.
The frequency.
Yeah, but uh, does that sound like a practical solution? That, because I do not know where is the mid portion of this
Yeah.
slant curve.
Yeah. Okay.
Okay, so what in practice I do is I measure the length of this flat portion, because this flat portion, okay, it is easier to determine where it starts and where it ends. Okay, because there is a discrete slope change here and here, right?
Yeah.
Okay, because see here it was a continuous slope. Okay, so it was difficult to you know mm, calculate, like where should I put my let's say spacing line. Let us call this spacing line. Okay, but when I go from the slant portion to the flat portion, okay, then it is easy to put. I can see that yes, this is the place where change has happened. Okay, so what I do is I measure the time period for the flat portion. Okay, so this I measure. Okay, and this also, in the reverse direction also I measure time for the flat portion, right?
Okay.
Okay, so both of the time will be the same. So let us say, for example, um, time of flat, the total time for flat, okay, I measure to be 0.1 millisecond. Okay,
Okay.
so now tell me what is the total time period of the back EMF curve?
So we are just counting all the flat lines.
Yeah, so basically this time
Time
period,
period for the flat lines.
yeah, of the total flat portion,
Okay.
in one cycle.
Okay.
Okay, so if we go here, this is one cycle, right? From 0 to 360 degrees. Okay, so in this one cycle, I measure how much is this time plus how much is this time. Okay, okay, so to do this, actually, what we need to know is how are this total time and the flat time related, right?
Okay.
Right. So we know that you know flat time was how much out of, it was for 240 degrees in how many degrees? Okay, if a total time period, by time period we mean one rotation, because in one rotation one cycle of back EMF happens. That much is
Okay.
clear,
Uh, okay. Okay.
right? So if the total is t, then this fraction of t is my flat time period.
Okay.
Okay, so it comes as what? 2 over 3 times t. So my total time period comes out to be 3 over 2 times flat time, right?
Yeah.
So simply we do not do. Total time period is 3 over 2 times zero point 0.1 millisecond. Okay. And that is 0.15, right?
Yeah.
Okay. And now if you want the frequency, that is 1 over t. Okay. So basically 100 upon 15. And how much is 100 upon 15?
Somewhere around.
Something around 6.666, right? Right?
Just yes, just a sec. Yeah. 100
Okay.
around.
So this
Yes.
much
And
hertz. Okay.
yeah, 6.6 hertz. Yeah.
Yeah. So basically that's how you calculate the frequency. Okay. Now if I just tell you that I have changed my velocity, changed my speed to 5 times. Okay. What will be the new frequency? You just multiply this by 5 times.
Okay.
Okay. It will become 33.333. That's just math. You can do math.
Okay.
Okay. So this is clear.
Yeah, I got it. Yes.
Okay. So now let us go to the third problem. Okay, this is just a simple, just a conceptual problem. Okay, that what happens to the magnitude and polarity of the back EMF of a BLDC motor if the speed is same but the rotation direction is reversed? Do you understand the question?
Yeah. I mean, it will rotate the opposite direction, right?
Yeah, eh, I, I'm giving you that it is rotating in the opposite direction.
Yeah.
Okay, so what will happen to the magnitude and polarity of the back EMF curve?
Polarity will change. Magnitude will remain the same.
Exactly. Okay, so basically, uh, magnitude same, because magnitude will depend on the speed only, not the direction of the speed. Okay, and
Yeah.
polarity will change because now the current will be generated in the opposite direction. Okay, so since current is going in the opposite direction, so the voltage difference would be switched. Okay, it will be reversed.
Okay.
Okay, so let us now do one like numerical problem for this. Okay, so are you comfortable with all these you know terminologies of BLDC motor? What is the phase winding and all?
Yeah, I know the concepts, but I don't know the mathematical part of it.
No, no, I'll show you the formulas and all, but you
Oh,
just know the terms, right? That are here, like what is the duty ratio? Do you know what is duty ratio?
no.
Um, okay. Do you know about the inverter?
Yes.
But no. Okay, three-phase inverter. Because you said you stopped after H bridge, right?
Yeah.
Okay, so let's see. So, it's- hmm. Okay, so what you have in H bridge is you have this. Yeah. So let us say that this is your DC power source. Okay, and then there is a controller. Okay, I'll denote it by C, right? And then there is your H bridge. Okay, I'm making it in this specific way for a reason. Okay, and it will be clear after some time. And how do we connect the motors? Like this, right? To the H bridge. Maybe
Yes.
this one.
Yes. Yes. Yes.
Okay, this is H bridge. Okay, so this is for a single phase motor. Okay, this is a single phase motor, right? There is only, you know, one pair of windings, right? So for three phase motors, what we do is, so basically this H bridge is an inverter for these kind of motors that have single phase.
Okay.
Okay, so now how do we control the H bridge? Okay, so how we control is using the controller, we change the timings at which we open and close these gates, right?
Okay.
Okay, so let us say that this battery gives us 12 volts. Okay, but I want to give only let's say 7 volts here. Okay, because of course 7 volt will correspond to some particular speed, right? Let us say
Yeah.
that 0 volt is 0 rpm and 12 volts is 120 rpm. Okay, let us say at 0 volt, basically it will not move because if you have 0 volt, then there is basically no current going into the windings. Okay, and at the maximum you have, let's say, you can go up to 120 rpm. That's fine. But now I want to move it at 70 rpm. What should I do? Tell me. Hmm. Okay, and I also give you that this transition is linear. Okay, basically your
Okay.
speed is proportional to voltage. Okay, so now if I want to run at 70 rpm, how much voltage should I apply, at these 2 points?
Uh, that is 120 minus 70 divided by,
I don't know why minus. See,
like it
uh,
will vary linearly, right?
yes, very linearly. So you have 2 points, right? Okay, so you want omega is equal to what will be there? It will be 10 times V. This is the equation, right? It fits both these points.
Yes.
Okay, so now if I want my omega to be 70, how much should V be?
Just a sec.
7?
Yes. Yes. Yes.
Yes, 7 volts. But my battery can only give how much? This is a DC
12.
battery, I can only give 12 volts. So how do I get 7 volts here? Should I just abandon hollow? Okay, so that is where PWM comes in, concept of PWM. Okay, so what you do is you say that yes, at once I cannot give it, 7 volts, but if I do like this, okay, this is my voltage, and this is my time. Okay, that if I give it 12 volts for some time, and then I cut off the signal, okay, and then I let it be zero, and then again I give it, I turn it on and then cut, again I turn it on and then cut. Okay, so basically the idea here is that in this one time period, okay, let us say that this is t, for how much time you have kept, this circuit closed, basically for how much time you have provided the voltage, high voltage. Okay, that is called the duty cycle.
Okay.
Okay, and let us say that this is your VG of the generator or the source. Okay, so if you are going from 0 to VG, okay, basically you are saying that you understand what a duty cycle is, right?
Yeah. Okay. I understand. Yeah.
Okay, so in this case, let us say V effective, okay, it turns out to be D times VG. Okay,
Yeah. Okay.
right. Now, uh, yeah, what will, how will this equation change if I say that for a duty factor of 0, okay, I want my V effective to be minus Vg, okay, and for a duty factor of 1, I want my V effective to be plus Vg, okay. So basically, what will be the relation between V effective and your Vg? In earlier case, it was just this, when you were only going from 0 to Vg. But now I'm telling you that I want to go from minus Vg to plus Vg. Okay, this was also from 0 to plus Vg. Okay, so how will this equation change, basically? Hmm.
Is it in a graph or just
Yeah, so basically this is also linear, right? This will also change linearly. I'm saying that if it is 0, yeah, basically I should give, yeah. It will also change linearly with duty factor.
okay?
Okay, so basically what I want is, when your, let us say this is duty factor and this is your V effective. Okay, so and this goes from 0 here to 1 here. Okay, so from 0 to 1, okay, it should go from like this. This is a line, okay. I know it looks curved. Minus Vg to
Plus
this
video.
is plus Vg. Okay, so yeah, what is the equation of this line basically? Because this will give me V effective for any duty factor.
Okay, the slope. I mean,
Yeah, the slope, and you need two things: the slope and this, constant offset.
okay.
Yeah. So let me remove this. Okay. So it will be something like this: A times D plus. Let me not write A. Let me write M. M is the slope. M times D plus B. Okay, where M is the slope and B is the offset.
Yeah.
What is M? Right. M is plus Vg minus of minus Vg. That is also plus Vg. Right.
Yes. Yes.
Divided by, like I told you, right, that this is 1 duty factor 1 and this is duty factor 0. So
Zero.
x-axis changing from what only? 1 to 0, right?
Yeah.
X2
So
minus
two.
x1.
Yeah.
So this
Got.
becomes 2Vg. Okay, and what is B? B is my offset. That is
My.
minus Vg. Okay, so this turns out to be 2Vg T minus Vg. Okay, so now if I take Vg common, it becomes 2D minus 1 times Vg. Okay, so this is my effective voltage for any given duty factor if I want to go from minus Vg to plus Vg. That is fine.
Yeah. Got it. Yes. Thanks.
Okay. So now you understand what is a duty factor also? Duty
Yeah.
cycle.
Yeah.
Okay.
I mean, it's a time
Yes.
when it is on and time when it is off.
Yes. The ratio of the time
Ratio.
for when it is off to the total time, not to when it is off, to the
Okay. Okay.
total time.
Total time. Okay.
Okay. Basically, if I say the time is 1 second, then if it is on for let's say 0.3 seconds, then the duty
Okay.
factor is zero point 0.3.
Okay, okay, okay.
Okay,
So
duty
total.
factor or duty ratio, whatever you want to call it. So here it is given that the duty ratio is 0.75.
Okay, okay, got it. Yeah. So, so like there's out of 100 seconds, like 75 seconds is on or off.
On. Okay, so out of 100 seconds, 75 seconds it is on, and 25 seconds it is off.
Okay.
Okay, right. So now I think uh, we can go to this problem. Okay, so basically the concept is more or less the same as DC, only the you can say the equations change. Okay, so people are coming. Okay. Okay, so this question is clear. Like, have you read this question? That we have been given the resistance, we have been given the magnitude of the flat portion that we just discussed. Okay, how it is used. Okay, so now see, for this particular case, K is 0.2. Okay, the DC input voltage we have been given, that is 100 volts, and in every 60-degree interval, the respective switches are operated at a duty ratio of 0.75. Okay, so yeah, we did not talk about the switches, right? So basically, in an H bridge, switches are like this, right? For a single
Yes.
phase. Okay. Now, if you have three-phase motor, so the inverter for a three-phase motor looks something like this. Okay. There is one switch, and there is another switch. Okay. So basically, there are three pairs of switches for three-phase. Okay, one for each phase. Okay. So these are connected to again your battery, okay, your DC source, and these three terminals basically at the middle of these, these are called legs of an inverter. Okay, so the mid terminal of each leg is connected to each winding of the your BLDC three-phase motor. Okay, now many people call it RBY, you can call them ABC, whatever. Basically, there are three phases, so there are three pair of switches. Okay, now you can think of it like, if you want to rotate this motor, at a particular speed, okay, then you need to give PWM at these switches. Okay, like in H bridge also you were giving PWM at these switches. Okay, because how would you make this kind of profile? You would have to turn it on and then off, on and off. So this on and off thing is being done by switches, right? And this switch is being controlled by my controller. Is that
Yes.
fine? Yeah. So basically, in this case, I will control the switching of these, you know, switches of each leg to rotate my motor. Okay. And how do I do that? I have a table. Okay. This commutation table, I won't draw the complete table now. Basically, you can, I'll just tell you very briefly. There are six different positions, in your BLDC. Okay. So for each different position of rotor, okay, you will turn on specific switches and turn off specific switches. This is just an example of one. Okay, and this switching logic will be such that this motor keeps moving in any given particular direction. Does that make any sense?
Yes.
Right. So let us say if this is 1 2 3 4 5 6. Okay, it is possible that in the starting I will only turn on switch 1 and 1 and 6 and the rest all are closed. Okay, and then when it goes beyond 60 degrees, basically why 60 degrees? Because we have an arrangement there such that it knows when it has crossed 60 degrees. Okay, because from three phases, okay, you can divide your whole motor into six different areas. You can say like this. Okay, like because in-depth theory you can refer some book, or like because it will take more time, then we won't be able to solve more problems. Okay, but if this makes sense, that yes, for each location, let's say for 0 to 60 we have a different logic. Okay, so for 0 to 60 we have a different logic, and then yeah, 0 to 60 we have a different logic. 60 to 120 we have a different, 120 to 180 we have a different logic. That way we keep going, and this logic ensures that the motor keeps moving. Does that make sense?
Yeah, okay,
Okay,
got it.
yeah. So basically, this is what it is talking about. In every 60-degree interval, the switches, active switches, are operated at a duty ratio of 0.75. Of course, if you want to change the, let's say, speed of the motor, then you will change what? The duty ratio. Okay, you will try to switch more faster so that your motor moves fast. Okay, and the operating speed is 60 radian per second. Okay, so now what we want to determine is the average value of armature current. Okay, now after giving everything here, why do you think they are interested in armature current? Why? Like, does anything important related to motors depend on armature current? You can think about this, and till then I will just show you. You think about this, I'll solve this question, and towards the end I will tell you the you know actual reason why we are interested in armature current.
Okay.
Okay, yeah. So okay, so how much is the phase winding that we have been given? That is, I think, 0.6 ohm, right? And the peak value of EMF, how much was it? 0.2 times omega, right? And what is our omega? It was given, right? 60 rpm. No, 60 radian per second, right? Good. It is in SI unit. 60 radian per second. So we can calculate our back EMF magnitude. That is zero point 0.2 times 60. This is how much?
12.
12 volt. Okay. And per phase, this is 12 volt. Okay. Because for each phase, this is the maximum, right? There are three different phases. Okay.
Yeah.
Okay. Okay. So now, like, this is also a result of three phase motors. So you can look up any textbook, you'll find it that, you know, the effective voltage, okay, basically the circuit voltage in any armature, okay, that can be written as the phase current times phase resistance times 2. Okay, how this comes, you should, yeah, refer a textbook. Times 2 times the back EMF. Okay, and this is our EF, right? So what we have been asked, right? What was asked in the question?
Armature current, right?
Armature current flowing in the phase windings, basically phase current. Okay, where is phase current in this? Here. Okay, so we want this, right? Okay, this is known, right? This is known because we have calculated this. Now we want this, the effective voltage. How do we calculate the effective voltage? Can you tell me?
Use the equation, right?
We derived this equation, right?
Yeah.
Yes. So this is what we use. Okay, because we see right that the EMF goes from plus to minus. Okay, so we need this also, basically our effective voltage to also go from plus to minus. That's why we use this one, 2D minus 1 times Vg. What is Vg? What is Vg in this case?
100.
100. Yes. And what is D? What was D? Duty
Uh,
ratio?
duty ratio, so 0.75.
0.75. Yes. Okay. So I can calculate my V effective as 2 times D, that is 0.75, minus 1 times what?
VG.
100. That is my Vg. Okay. So this comes up to be what? 1.5 minus 1, that is 0.5, right?
Yes.
So my effective phase voltage is
50.
50 volt. Okay. Now once I have this, I calculate IPH?
Yes.
Can you try and calculate and tell me how much is the value of phase voltage? Hmm. Did you get? Okay. So when you do this arithmetic, so you'll get that the phase voltage is 21, approximately, 21.67 amperes. Okay. So this much is the phase current that it was asking for. Are you also getting the same? Yes. Hello, am I audible?
Hello.
Yes, Venkat. Venkat.
Yes, sir. Sir, the answer is supposed to be 2.16, right?
No, no, it is not 12. It is 1.2 here. This is
Oh,
1.2.
okay, okay, sir. Sorry,
Yeah, because
my
this
bad.
is two times phase resistance, right? And your phase resistance is 0.6.
Yeah, 21.6.
Yes, sir.
Okay, so you're also getting the same thing.
Yeah, you got it.
Cool. So basically, this is how you calculate phase current. But now again to the previous question, why do we need phase current?
To get to know maximum speed.
No. See, this is the thing about motors. Speed does not, depend on current. Okay. So basically, your torque of the motor is related to phase current by this.
Torque, okay.
Okay. So the torque, how much torque you can apply from this motor is determined by this equation. And this Ki is, again, it is called the torque constant for the motor. Okay. So now again, the same thing I said earlier, that you are always interested in inverse problems. Okay. You know how much, so right now, if you know this current, and if you take Ki for any motor, it is in the data sheet of any motor, you can calculate how much torque, right now it is at time. But that is not what you want. What you want is, you want to, let's say, rotate some, uh, what should we say? What should we rotate? Let us say there is a robot, there is a robotic arm, and you want one of the arms, to apply a torque of 2 Newton meters. Okay, so now for there, for the torque to be 2 Newton meters, how much is the duty cycle that you should provide? Okay, because everything else is given. Okay, that let's say at this speed and at this voltage, I want 2 Newton meter torque. Okay, so from there I calculate the duty cycle. Okay, that how much, for how much time should I keep my inverters on and off? Did you get it? Like, does that make sense? Um,
Yes,
oh, okay. No,
got
like
it.
you can say no. I'll explain more.
Can you tell it again?
Yeah. So what I was saying is, you know how much torque you want to apply at a joint.
Okay,
Okay, because this is a requirement. This comes from your control. Okay, control says that at this joint apply this much torque. How do you apply this much torque? You know that torque is related to the phase current by this equation. Okay, so now from torque you calculate phase current. From phase current, you know, you calculate your effective voltage, that how much effective voltage should be there at the inverter, for the torque to be whatever specified. Okay, and what controls the effective voltage? The duty cycle.
okay,
Okay, and basically duty cycle is the only thing you can control from your microcontroller,
okay,
right? So using the duty cycle, we are controlling effective voltage. From effective voltage, you're controlling how much current should be there, and from current, you're controlling how much torque should be there. That makes sense?
yeah, got it, sir.
Okay. Okay. So like in this year assignment also, like for this week, you have similar kind of problems. Okay, and there are some problems that include, that this much number of poles is given. What is the, let's say, frequency of the Hall switching, of Hall switches? Okay, do you know about Hall switches?
What?
Do you know about Hall switches?
No.
H. Okay. So basically, I was
Which?
telling you, right, that somehow we know that our rotor is in 0 to 60 degree, or from 60 to 120 degrees, right?
Yeah.
So how it knows is through these sensors. Okay, Hall switches. We call them Hall switches. They are basically Hall effect based sensors. Okay,
Okay, okay,
so yeah, so basically we use three or six, or however many we want to, use these switches. Generally, we use three. Okay, and then based on the output, basically signal of these switches. Okay, because let us say that this is the magnetic field of the rotor. Okay, and this is the position of these three sensors. Okay, so these are like binary sensors. Okay, binary, basically they can either give one or zero. And when do they give one? Whenever a strong magnetic field passes near them, they give one. Okay, and
okay,
when it goes away, they give zero. Okay, so using these three, okay, I can form a logic. Okay, that if my, output is 100, then it is between 60 and 120 degrees, right? If this is 1, this is 0, and this is 0, then probably my rotor is somewhere between this area, right?
yeah, got it.
Okay, so similar to this, we form for every 60 degrees. Okay, so Now, you know what Hall switch is, and what were we discussing? Like I forgot where the Hall switch reference came from. Hmm. Okay, so you might have some of the questions that involve that this rotor is rotating. Okay, so what is the frequency of? Basically, they will tell you to calculate the speed. Okay, or they will tell you to calculate the pulse frequency of the Hall switch. This is different from the back EMF. Okay, this is of the Hall. Let's do it. F of H. Okay, so the concept here is that in a motor there can be multiple poles, right? We draw it like this, that there is a motor and then there is a north and a south pole. Okay, but in reality there are multiple magnets, right? If you have seen a magnet somewhere. Okay, so like if we try to draw them inside only. Okay, there are like this also, right?
Yes, yes.
Do you know about this, that there are multiple poles
Yeah, got it.
in a
Yeah, I
single
know.
motor? Yeah. So what will happen is, now if there are multiple poles, okay, then in one rotation there will be multiple pulses in each Hall sensor. Okay, because let's say if there was only one pole and there was one sensor here. Okay, then in one rotation there would be only how many? One switches, one switching. Okay, you get this?
Yeah, I got it. Yes.
Okay, so yeah, so let us say for one it was this. Okay, for one full rotation. Now if there are two pole pairs, okay, basically in this case I have drawn, in which there are two north and south pairs, there are how many poles total? Four poles, right?
Yeah,
But how many pairs?
two.
Two pairs. Okay, so if any question asks that the rotor is rotating at, let's say, omega, then what will be the switching frequency of this Hall effect? This is your Hall effect sensor output. It can be either 1 or 0. Okay, and this is time. Okay, and the frequency basically of this signal gives you the reading of angular velocity, right?
Yes.
Okay, but you were getting angular velocity above, like before also, from your back EMF curve. So why do you need Hall switches then?
To know the like magnitude and of magnetic field or something.
No, no, no. See, we were using an extra equipment for measuring back EMF, right?
Yes.
Okay, but can we use it always? Can we always use it? Can we always put an oscilloscope, beside a motor?
No, no,
No, right? That
no.
is why we use this Hall effect based sensor to measure the speed of this rotor. Okay, basically now to measure the speed of the rotors, we are using Hall sensors, but we know that the change in Hall sensors happen because of pole pairs, right? So frequency of change, right, of any Hall sensor would be equal to the number of pole pairs. Okay, this is pole pair, right? Just remember, this is pair, pole pair, multiplied by the speed. Okay, any question? Like this is the formula. You can, I mean, it makes sense also because if there are more pole pairs, then the frequency of switching will be more for the Hall effect output, right?
Yes.
Let us say that we keep omega constant, but we increase the number of poles, right? We increase the number of poles. Then, of course, for the same omega, we will have more switches like this, right? So this is the equation that relates the frequency of the Hall effect output to the number of pole pairs and the speed of the rotor. Okay, and the
Uh,
speed should be in SI units basically. Your no, wait, it should not be radian per second. It should be revolutions per second, right? Because in one revolution you're taking note of frequency, right?
yeah.
So your omega should be in revolution per second. Basically, if you have been given that your omega is, let's say, some W, capital W RPM, okay, because usually you are given omega in RPM, right? Okay, so you just do W over 60 multiply by the whole pair. Make sense?
Yes, I got it. Yes.
Okay. Yeah. So that, like, these kind of questions you might have in your assignments, I guess. This kind and the one that we discussed. And now again some conceptual questions related to the construction of BLDC. So I told you about the inverter, right? Three-phase inverter and the legs of the inverter. Okay. So you can also answer this question thinking about H bridge actually, because the concept is same. Okay. So let us say if you're not comfortable with three-phase inverter, you know, tell me why, because in this H bridge also there were two legs, right? One leg here and another leg here. Okay. So if you like did not know till now, I am telling you now that these, what is that? Yeah, the two switches on the same legs, right? You cannot close them together. Can you tell me why? Okay. Yes. Any idea? You can also say that no idea. You don't know. Yes.
No, I don't have.
Okay. So basically, you see, let us go to H bridge. Okay. What do we usually do with H bridge? Okay. How do you know? You know how an H bridge works, right? Okay. You close this and this switch. Okay. So the current will flow from here to the motor, and from motor it will go here, and then it will close the circuit like this. Okay. So the current in the motor will go in this direction. Okay. This
Yes.
much makes sense.
Ah,
Okay.
yes.
Now let us say we close this switch and this switch. What will happen? Okay. Now the current will come like this, go into the motor here and go here like this. Okay. So in this case, the direction is reversed, right? Now,
Yes.
since direction of current is reversed, so the direction of rotation will also be reversed.
Yes.
Okay. So using H bridge, you can, rotate your motors in different directions using this logic. Okay. It only has this logic that either you close these two or you close these two. Now, what
Okay.
happens if I close these?
There'll be no flow of current, right?
Yeah, there will be flow of current, but not in the motor.
Yeah.
Okay. Basically, current will come here, and go straight like this. Okay. Basically, your battery will be shorted. Okay. So now this kind of arrangement can either, damage your inverter, damage your battery, damage your house, maybe. something catches fire. So this is bad. Okay, same concept, same thing we use here. Okay, because if we close this and this, all the current will come and go in this one leg. Okay, and it will damage the inverter. Okay,
Yes.
so that is why we never close the switches on the same leg of the inverter at the same time. Okay, at different times, if one is off, one is on, one is off. Okay, that is allowed. Okay, but at the same time, both of them should not be on. Okay, and okay, do you know what PMSM motors? No, right? Pratyush, do you know about PMSM motors? Okay, so see, the main difference between BLDC and PMSM motors is in their back EMF profile. Okay, for BLDC, we know that it is trapezoidal type back EMF, right? We discussed it.
Yeah. Yes.
Okay, so for PMSM motors, the back EMF profile is sinusoidal. Okay, it varies like a sine wave. Okay, so now once you know this, that you know their back EMF profiles are different. So do you think we need different types of inverters for these motors? Like everything else is same, only the back EMF profile is different. Okay, so basically what we do is, okay, why we have this logic here, we are basically compensating for this back EMF. Okay, how much back EMF is there, we are overriding it. Okay, so that our motor can keep running smoothly. Okay, there are some ripples, you know at the where there is a transition. Okay, otherwise we want it to keep running smoothly. Okay, so in this case I have to you know switch my inverter with something. Yeah, like that is just example. Ripples actually, yes, ripples occur at 60 degrees because as we said, at each 60 degree you're changing your commutation. Okay, so when you change your when you switch different, when you use different switches, that is where the ripple occurs. Okay, so basically you just change your logic, okay, of how you switch those legs. Okay, in this inverter, how you switch these in case of BLDC, you switch these such that your voltage profile is compensating for the back EMF. Okay, and then for PMSM you switch this such that your voltage profile is compensating for this kind of sinusoidal back EMF. Okay, so both of these can be achieved from same kind of inverters. Okay, what you need to change is just your PWM value. Okay, because how you control the switch is up to you, right? Now if you control the switch in a different way, you will have different type of behaviors, basically different type of voltage outputs here, right?
Yes.
That, yeah, so that is why we do not need different types of inverters for BLDC and PMS motors. Same inverters work, control is different for both. Okay, like, that is it for from my side this week. If you do not have any questions from today's session, like, you can leave. Thanks for attending.
Thanks.
Yeah, yeah, sure.